a few teams that are willing for a technical award. Today, it's been a great day. We already had a few keynote speakers, and we learned a lot from them. And also, we had the opportunity to watch the podium session of two teams, Aerozono and Team 37, and Capital Rocket team from Brasilia, University of Brasilia. It was amazing. So now I will pass the word to João Pedro, and he will talk a little bit more about our schedule for today and this evening, and also introduce our next speaker, Caius. So, João, the word is with you.
Whoops. Hello everyone, welcome back to the evening part of the Latin American Space Challenge online edition. And for this evening, we will have some proposed talks and of course some podium sessions. We will start with Caius from Alba Orbital. He will be talking about our democratization of access to space. They do a very good job with pocket cubes, and he will of course talk to you more about that. We will have Adam Trumper from Launch Canada talking about the Launch Canada Rocket Challenge. We'll have as well Ramos Pedersen from Danstar. They launched a very cool liquid rocket from Euroc this year. And we have the podium session from Team 03, that's Club Universidade de Desarrollo en Sistemas Espaciales. That is from Mexico. And we have Minerva from UFRJ from Brazil and Projeto Júpiter and Topos Projetos Espaciais. And then as closing, we have Ricardo Freire from Comai. So now I will pass the word to Caius from Alba Orbital that will present to you some really great things about our Alba.
Thanks for the introduction and thanks for inviting us. We're really pleased to be here. Heard some really good stuff from some cool teams. So I guess I'll crack on with it. So my name's Caius, I'm from Alba Orbital. So our kind of presentation here today is about democratizing access to space with pocket cubes. So I'll give you a bit of information about Alba Orbital. So we were founded in Glasgow, Scotland in around 2012 and opened our second office in Germany last year, just after our last launch. So we now have the world record for the most pocket cube satellites deployed in orbit compared to anyone else worldwide. And we're going to be breaking that record again in 2020 with our next launch, which I'll talk about in more detail. As an overall, we provide picosatellite platforms, ground stations, and launch opportunities at a much lower cost to make sure that everyone has access to space. And sort of our kind of client base includes Stanford, Carnegie Mellon, and lots of other universities worldwide. So as I said, our mission and our vision. Oh, yeah. Our mission and vision is to democratize access to space, as I said before, but with pocket cubes. And so I'll tell you more about pocket cubes in a minute. So that's been our main goal since founding up almost 10 years ago, very close to 10 years ago, and we're the only company who's been focusing on it. So what are pocket cubes? Pocket cubes are tiny satellites comprising of 5-centimeter cubes, and they get their name from being small enough to fit into your pocket. So they're democratizing access to space by removing economic barriers during both development and launch. So here's a little bit of size comparisons to get a mental image of what they're like. So on the one hand, you've got the 1P, which is the smallest of pocket cubes, which are about yay size. And they're about 5 by 5 by 5 centimeters. Then you move on to the 2Ps, which is like the Unicorn 1 here, our first satellite. And then you move on to the Unicorn 2, which is a 3P. So that's about 5 by 5 by 15 centimeters. and that's the structural chassis of it. But we've got a picture of a mug next to it, so you can get some sort of feel for the idea of what the size is. So, like the revolution in computing revolution that we've seen with PCs, computers have went from massive mainframe era computers that would take up an entire room to process very little data into computers that you can hold in your hand and access to the internet, and now that's democratized knowledge for everyone. So that's an example of the sizes we've got here. So we've got the old era satellites, CubeSats, and now 1P satellites. So that particular one is built by a Turkish team who will be launching with us this year as well, Grizu 263 from Zonguldak University. So how are pocket cubes allowing people to have access to space when they never could before? Well, most people don't have a NASA-sized budget, so the best thing about pocket cubes is that they've got really low hardware and development costs, which brings down the entries to space. So they're built using components from off-the-shelf COTS, which can be used taken from smartphone electronics and all sorts of different places. There's a lot of knowledge to be shared between the developer community. So there's a lot of open source designs out there, and there's some great pocket cube kits out there from companies like BH Dynamics, and I've seen recently the PION labs are starting to provide. And the launches have really brought them down, because launches is usually priced by their weight. So it costs more than a kilogram per gold per kilogram than it is to launch. So these are 1P would only be around 25 grams in weight, and that's significantly lighter than say a CubeSat, which is quite bigger. So a 1P would be 25,000 euros, and a 1U would be 100,000. So the fact that all these costs and the smaller form factor allows means that more organizations who wouldn't otherwise be able to go to space have the ability to entry now. And that also allows for larger satellite constellations. As you can imagine, that leaves more money in your pocket to launch more satellites. So, for example, you could launch 4 for the price of 1. And it also leads to better and faster iteration and innovation cycles, as you have more room to make mistakes. You have, it's not as high risk as putting all your capital into one satellite that might break. There's faster iteration processes. So this is a quote from one of our customers who will be coming on to our next launch. It's Felix Paez from AMSA EA in Spain. He's the president, and you can see his satellite on the left, which is a 1.5P. So he said when he started thinking about building a pocket cube as a team, a satellite as a team, the first thing he saw was the CubeSat standard, which he thought was the only thing available to them because it seems to be that's the way. So that would cost them over 100,000 euros, and that's something that most people just can't put the money up for. So when they heard about pocket cubes, they were really excited because they were cheaper to develop and to put into space, as I've said. And until now, only major organizations, big companies, and some universities can maybe use the funds to fly satellites. So they'll be flying 2 1.5Ps called ESAT-2 and Hades, and I'll be talking a little bit more about specific applications later. So you might think, okay, cool. Pocket cubes, they're cheaper, but they're smaller. Do I have enough space to actually do anything with them? What are they capable of? So as you can see, they've got a vast array of missions that you could pull off. Some have been completed in the past, some are just still about to fly, and it's a really exciting time for pocket cubes, really. So it spans from everything from education to Earth observation, weather, and more. In an example of Earth observation, you have so many use cases alone. For example, you could really help fight fires. You could help out checking on GDPR per nation, tracking illegal fishing. These possibilities are endless. But I'll just go into more details. So pocket cubes are a great utility for universities. The low cost of the launch materials mean they're much more affordable to schools, universities, and colleges, and they don't require excessive facilities. So, for example, the first pocket cube ever launched was called $50 Sat, and going by the name, you can guess how much it costs to put the hardware together. So, as more successful pocket cube projects have demonstrated the viability of low-cost picosatellites in low Earth orbit, it's becoming more apparent to universities that this is something that they can do. And so here's the Satduino team at the third PocketCube workshop, who are based in Argentina, as well as another American counterpart out in the USA, who are also building PocketCubes in the community. So giving students a hands-on approach to engineering and letting them learn that way gives them so much motivation, drive, and applicable knowledge. And it's even nicer to know that their work will be going to space. So you can see it's not just exciting for students, but it's exciting for the whole nation when someone says, I'm going to build a satellite and I'm going to launch it. So this is all the press from off of one team, the Turkish team, Griza 263A, that I mentioned earlier on. And this is a university team out in Hungary who launched with us last year, now being put onto TV shows and such. Like, I'm not promising this is a way to stardom or fame, but you know, it's certainly interesting and fun. So here's an example of an RF spectrum monitoring case study. This is with SMOG-P, who I talked about from the Hungarian university. They were successfully put into orbit via Alba Cluster 2, and they broke world records as the most successful 1P mission. And they've actually, that tiny satellite measuring about this size, managed to take well over 2,000 measurements of electro-smoke pollution across the world. And they've managed to make an interactive map, which is really interesting. So if you're interested in that, you can read more about the case study. So there you can see the satellite there, as well as all the data points they can take on. And so they recently came down out of orbit recently. So another advantage of PocketCubes is that they minimize the risk of being space junk due to the fact they've got short deorbiting lifetimes. So that's been accounted for as well as emerging propulsion systems that are coming out with companies like, I forget their name, Porkchop. That's another one in AIS, Applied Ion Systems. And different ideas for our spectrum in this world is ADS-B payloads, which can be used for plane tracking. So a couple of PocketCubes have aimed to do it. And AIS payloads for ship tracking. You could pull off IoT constellations as well, Internet of Things, to connect devices, which could be used for so many applications. For example, smart agriculture and smart cities. There's actually a PocketCube team out in Argentina who are also aiming to do a constellation of IoT for the sake of smart agriculture. So it's good to see how these tiny little things can go to space and help our lives on Earth. So as I said, the mission possibilities are really endless. I could go all day, but I'll move on. So you want to know how Alba can help you get to orbit after you've kind of thought PocketCubes are cool. So we're the world's leading PocketCube company. We've been going for almost 10 years, and our team's got more experience delivering extensive commercially focused picosatellite services than anyone else, as it's really been our niche, and we're kind of really proud of the fact that we're helping more and more people get to orbit. So we provide everything end-to-end for users, including picosatellite platforms known as Unicorn 2, launch services, deployers, ground station solutions, and additional add-ons like licensing, testing, and consultancy. So Unicorn 2 is the second iteration of our initial PocketCube platform, which was Unicorn 1. So Unicorn 2 is our flight-proven second generation 3P PocketCube, which was developed in support from the ESA, European Space Agency. So our goal with the PocketCube was very similar to how the mainframe computers came down from being one massive room to a little handheld phone. So in that case, we tried to make the performance comparable to a 3U CubeSat. So we've managed to fit on 20-watt quadrupole deployable solar panels, world's smallest active pointing system, key electronics all integrated into a single backplane, all under the weight of 750 grams and measuring approximately 5 by 5 by 19 centimeters. So these are similar to the other ideas that were available on the screen, but the good thing about the Unicorn 2 is that it's a modular platform, meaning that it could take any sort of payload you want. So if you don't want to build a satellite and you just want to have your payload put in orbit, we're able to put that on. So we have about 2P's worth of space on our Unicorn, and it's a very plug and play approach, simple. So you've got that payload and we can take it on board. And as I was saying, we've got sample Unicorn 2 payload boards, just in case you want to have a play around with it, just to see if you could develop a payload that could fit into Unicorn 2. And they're free, so feel free to get in touch at my email or hit me up on LinkedIn, and we're more than happy to have a talk about any sort of missions ideas you might like. So now that you've actually procured a Pocket Cube, whether you've developed one yourself or you decided to buy one off the shelf, now you need to launch. So that's why we've introduced Alba Launch clusters. So Alba Launch clusters was born out of a necessity for Pocket Cube developers to actually reach space, and there wasn't a lot of infrastructure there before we developed the Alba Pod, and Pod stands for Picosatellite Orbital Deployer. So we provide low-cost launch opportunities on a flight-proven system, and we provide the lowest prices on a reliable system that's actually flown quite a few times. So to date, as I've said, we've successfully deployed more Pocket Cubes than any other organization worldwide, and we're just going to keep launching. So the Alba train doesn't stop, as cheesy as it sounds. So our previous launches have all sold out, but our cluster 4 for next year is shaping up to be really exciting. We've got lots of launches lined up, lots of satellites lined up for there. So there you can see a picture of the rocket from Rocket Lab that we were on, launching from Mahia in New Zealand. And there you can see the Alba Orbital team, our mechanical engineer, our CEO, and another mechanical engineer sort of putting that pod on the rocket, ready to go. So our prices kind of start for 1P, which is about here. For 25,000 euros, a 2P would be around 40,000, and a 3P would be around 60,000. So there are sort of room for discounts if you're able to be an educational sector and you want to go for multiple launches. We can do up to 20% off, and that's we just want to help everyone get to space. So this is the Alba pod I was talking about. It's the world's most advanced space-proven Picosat deployer. It was space-proven as of last year, and it's the lightest pod available. So that means that we're passing on any savings made from the mass onto the costs. So it's suitable for 1Ps, 1.5, 2P, 3P, and it could be integrated onto any launch vehicle. So the way that Pocket Cube launch works is that you tend to ride share, which is like piggybacking off the back on a bigger satellite. So it means that you get to spread the cost between all the teams who are going, and you don't have to take, all the space on the rocket like how you would with maybe a bigger satellite would do. So if you were to come along and say you wanted to integrate and launch with us, we would take you to our Glasgow, or you can ship your satellite to us, and we could put it in the pod here. So here you can see all the pods from the Pico satellites from last year, and that's the outside. Oh, seem to have computer issues at the moment. Video seems to be tricky. I had a little teaser there, but it's not working, it seems. Okay, that's not working. So our next cluster, it will be in 2020, hopefully the end of December if it doesn't slip. So that's a picture of the integration there from the TU Delft team and Alba Orbital with their 3P. And that was a really big press release, and a lot of people got to see it, which was cool. So it's named that time of year of that mission. So it's the first annual back-to-back annual Pocket Cube launch, following on from our last one at the same time last year. So it'll be the history's largest Pocket Cube launch to date. So there's 9 Pocket Cubes aboard SpaceX Falcon 9, and we've got Pocket Cubes from all across the world, including America, Spain, Netherlands, Israel, Turkey, and more. So there's our Alba pods ready to be integrated, all fully loaded. The team getting ready to send them off. 3 satellites, all in the tiny Alba pod, and the Turkish 1P that I was talking about earlier. So kind of our future ambitions, we plan to go much bigger. So we want to service the needs for bigger constellations. So we've kind of come up with a 96P, which will be able to fit about 96 of these 1Ps or 32 3Ps. So that's kind of what the need is there for. So to service this sort of constellation, we've had to think bigger and put a lot of satellites all into this deployer. So hopefully as more demand increases, we'll be able to see more and more pocket cubes going up. So we, in addition to launch and platforms, we also do ground stations. So once you've launched your satellite, you'll need to communicate with it. So we offer this as a dedicated package, as well as a sort of subscription. So Alba Connect is a fully deployable, rapidly deployable ground station, which supports UHF and S-band frequencies. It comes with a trailer and lots more, so we can modify it to your needs, but that's kind of the standard. As you can see, all the benefits and features. I've mentioned full rotor control, trailers, solar panels. And you can see a picture of it here in our sort of Glasgow base before we move it off to Germany, which will be done by the end of the year. In addition, we also offer testing, licensing, and training and consultancy as part of add-on services, just to save you time and capital. So, for example, licensing is something that a lot of people just tend to underestimate. You know, you're so caught up in developing your pocket cube and excited for the launch that you don't tend to see the paperwork that actually goes into it. And, you know, some of it is quite scary, as the fact, like, on the long side, it might take you 7 years to put the paperwork together. That's what the sort of ITU, IRU, I think. I'm not sure in the particular license of this one, but it can take up to 7 years and very much close to 6 months at the fastest. So if you just want that kind of time saved, we can help you out. And we can also help you out with testing in terms of environmental qualifications, vibration tests, and training and consultancy. So if your university or your organization want help from experienced picosatellite engineers, we can come out to you and, you know, meet you and help you with a hands-on approach. So it's tend to be quite bespoke. So if you want that, you can come to us for prices about it. But last year, our CEO managed to fly out to Stanford to sort of meet the team there. And this year, even go out to see the BYU team. So we've got a growing client base, which is exciting. More and more demand for pocket cubes. So there you can see an example of who we are associated with. We've got over 25 customers in over 10 countries, including Stanford. You can see there 1P pocket cube going into our orbital deployer, Alba deploy. Carnegie Mellon, which is a 1P again, and TU Delft, who will be launching with us this year. So you can see some reviews. So this is the SMOG team. They were really happy that we managed to put two of their satellites in orbit without any problems, and that we contributed from end to end to help them make sure their mission went successfully. And as of recently, they spent about a year or two in orbit, just about a year, and they've just come down recently. And TU Delft really like the fact that we're one of the only companies whose our main focus is pocket cubes, so that we are easy to communicate with whenever they have specific problems. And we are the only company with a qualified pocket cube deployer. So that means that you've got a certain confidence about your satellite deploying without any issues. So in addition to that, if you want to learn more about pocket cubes in general, I do really recommend coming over to our pocket cube developer workshops. So this is where you can make connections with other satellite developers and hear lots of engaging talks. So for example, this was a talk done last year by Zach Manchester, who's a professor at Stanford University and helped pioneer the chipsats, which are satellites even smaller than pocket cubes. But unfortunately, due to FCC licensing, they're kind of banned because they're too small. But pocket cubes have been approved time and time again. And this is also the Satduino team, which I've mentioned earlier, based in Argentina. They came to our talks and, you know, they had a great time taking pictures and such. And it's also a rare place where you can get a hands-on look at actual space hardware. And when I say hands-on, I mean quite hands-on. As you can see, the ESAT team are able to see our deployers, and some other companies have been able to share their pocket cubes. So it's like a really nice environment. So if you ever want to come along, you can register for our next one, our website, the Pocket Cube Workshop website, or you can submit an abstract if anyone from here who's been developing pocket cubes would like to have a talk. So we'll be putting out lots and lots of helpful guides and blogs, and as we always do, for example, we've got blogs on how to develop satellites, how all the sort of specific niches that are in there, as well as just kind of more fun stuff like our PR updates and exciting launch announcements. So you can follow us on Twitter and LinkedIn and Facebook as well. Or you can come and contact us, and that's our phone number, and that's my email. That's
So yeah, we have here. Thank you again, guys, for your talk. We were very pleased with everything that you share with us from what Alva is working on. It was awesome to see the development of that 96 Pocket Cube deployer. So that was something that I haven't seen before. But we have a question here from Roger. If my team has a Pocket Cube ready, what is the earliest opportunity to fly with Alba?
So that's kind of an exciting question on our end, because we're kind of just looking to increase our launch cadence. So the earliest flight available at the moment is Q4 2021, so about the same time next year. But the thing about that is, it's been a very, very popular flight, so you need to kind of get it booked in soon. But hopefully, if more and more demands, if it keeps going that way, we'll announce something sooner as well.
Okay, and another question is, did Alba already supported or is planning to support any Latin American Pocket Cube to be launched?
We're in talks with some teams. Yeah, I can't say too much at the moment, but when we get our announcement out, you'll see some things.
I'd like to thank you again, Caius, for being here, presenting for everyone that was online and everyone that will see this recording later. We plan to later cut some the presentations and upload them to our YouTube channel so they can be standalone presentations, smaller presentations, of course. So everyone can watch specifically and comment on what they liked. But on behalf of LASC, I thank you, Caius, for again presenting here, and we want to hear from Alba soon. Thank you.
All right, thanks very much for inviting me, and good luck to the rest of the teams.
Thank you.
everyone. We are back with our 2020 Latin American Space Challenge Conference. It's an amazing event. We are having a lot of keynote speakers from all over the world. We already had the Brazilian Space Agency director, Paulo Vasconcelos, the CIO of Embraer X. We had also Caius from Alba Orbital, and now we are going to watch and hear more about Launch Canada and student rocketry, pushing the limits with Adam Champur from Canada. It's an amazing opportunity to hear about an other perspective of the space sector and more focused on rockets from Canada. Adam, thank you so much for accepting our invitation, and thank you for giving your time and investing in this presentation.
My pleasure. Thank you so much for inviting me, Calvin.
Nice. Thank you so much. So the word is with you, so you can start your presentation. Thank you so much.
All right. Thank you. That sounds great. So my name's Adam Trumper, and as Calvin mentioned, I'm the founder and president of Launch Canada, but I do a lot of different things, actually. So my day job is at Pratt & Whitney Canada, where I work as a concept designer and integrator on aircraft turbine engines. But during pretty much every other spare moment I've got, I'm heavily involved in the world of rocketry and space launch. And that includes both amateur projects that I do on my own, and you can see some of my my liquid rocket engine work shown here. But I'm also really heavily involved in the student rocketry community. In addition to founding Launch Canada, I'm also on the technical advisory board for the Spaceport America Cup, where I run launch operations and flight safety for liquid rockets. And if you've heard of the Base 11 Space Challenge competition to launch a student-built liquid rocket to 100-kilometer altitude, I was the technical designer for that competition, and I'm the co-chair of its safety council as well. Now, we're at a really exciting time in the development of the space industry, and I think we all know that this industry has been changing very fast internationally. We're seeing increasingly new companies and new countries becoming more prominent in this industry. And we're seeing a growing shift away from space being something that is just done by big national governments and towards something where actually entrepreneurial companies can play a leading role. And of course, everybody is familiar with some of the big names like SpaceX and Virgin and Rocket Lab and Blue Origin. And there's a whole long list of other ones. We're also seeing many of these companies starting up in countries that were not always big players in the space industry in the past. You know, Rocket Lab out of New Zealand, for example. The United Kingdom, Australia, Luxembourg, they're all really taking a step onto the scene. And Canada's in a really interesting situation because Canada has been heavily involved in the space industry from pretty much the very beginning. But we have tended to focus on a relatively small number of specific technology areas. So we're well known for space robotics, we're well known for our astronauts, we're well known for telecommunications and remote sensing, you know, all of these capabilities that tend to be important for a very large country like Canada. But historically, there has not been a lot of support here for things outside of those areas. And you'll notice I don't have any pictures here of rockets. Rocketry, and particularly larger rockets, space launch vehicles and things, have not been Canada's areas of focus. And I think it's been very easy for countries like Canada to slip into this mindset that says, you know, we're very small, we can't do everything, so let's just keep doing what we've done in the past. But that usually is a really limiting way to approach things. And fortunately, we've seen that starting to change here. And a lot of what's been changing it has been students and other amateurs who have been seeing what's going on internationally, are inspired by it, and want to be able to take part as well. So unlike the past, where usually it was government requirements and priorities that drove the development of space capabilities, With rocketry, we're seeing it going the other way around, where it's students and others who are excited about this and want to take part who are just doing it anyway. And that includes people like myself. For about the last 12 years, I've worked in my spare time designing, building, and testing liquid and occasionally hybrid rocket engines and developing all the capabilities I need to do that. And increasingly, doing bits of consulting and contract work on the side related to this. But a major part of this whole field of grassroots or amateur rocketry internationally has been you guys, the students. And I think, as you all know, the Spaceport America Cup, formerly known as the IREC, has been one of the leading rocket competitions in the world. And for many of us, that gave people their first opportunity to really be able to get involved with this. But it's spread far beyond that. It's become a genuinely global phenomenon, and this event today is a perfect example of that. And Canada has been very much a big part of this as well. So the Canadian teams usually make up the largest group of non-US teams at the Spaceport America Cup. They've done incredibly well at that competition for a very long time. And it's gotten to the point now where we've got more than 20 university rocket teams right across Canada, with probably more than 1,000 actively involved students. So this is becoming a real movement, and it's been really cool to see that happening. But while in Canada and in many places, rocketry is sort of a new thing, amateur rocketry is not actually all that new globally, and it's also not a strange fringe activity. If you go back to the very beginning of rocket development in the early 20th century, it was almost entirely driven by amateurs and students and people who weren't just doing this as part of a large company or a government research lab. Robert Goddard, who invented the liquid rocket, which is why we have things in space at all, was a college lecturer doing this in his spare time. Werner von Braun, who became the architect of both German rocket developments and later the United States' space program, got his start as part of an amateur rocketry group in Germany called the VFR. His Soviet counterpart, Sergei Korolev, got started exactly the same way in the Soviet Union. So people doing rocketry in this way aren't just some crazy fringe. They're literally the reason why this industry exists. And now you guys, the students in Latin America and around the world, are part of this very same thing. So in Canada, because this is such a new area, Launch Canada was formed to try to support this, and we're taking a very broad perspective of exactly how we do that. Obviously, our big goal is to be able to create more launch opportunities for amateur rocketry here in Canada, where currently not too many of them exist. But we're trying to go well beyond that. Safety is one of our major focuses. So as everybody knows, rocketry can be hazardous, and it's also a very specialized area of engineering. So we work hard to make sure that students who want to take on these types of advanced projects have access to the resources they need to be safe and successful at it. So that's an extremely important area. And it's even more important because many universities don't have a lot of experience with the practical side of rocket engineering and testing. And so we want to make sure that students who are in that kind of position don't have to go it alone and learn all this stuff the hard way. Innovation is a major focus of ours as well. We want to help to incentivize the development of significant new rocket and space launch technologies and capabilities so that hopefully student rocketry doesn't have to just stay student rocketry. It can actually lead to much bigger things going forward. And we've already started to see that. In Canada, we've got several startup companies now that are working towards space launch that literally exist because of student rocketry. Either they were founded by former rocket team members, or else they hire almost exclusively from the student rocket teams because right now this is where that talent pipeline exists. So we really want to work hard to facilitate that. Education in general is a major focus of ours. So we want to be able to use student rocketry to help students to gain the most experience possible so that they can go off then and start their own company or get a job in industry, but get that job being a much more knowledgeable and experienced person than they would have been otherwise. But we're also going beyond that, and we want to use rocketry to try to educate the general public as well about the importance of space and space launch. So these are some of our really big priorities. And of course, we also realize that we can't do this by ourselves. And so partnership and collaboration is a really big focus as well. So we want to both help the teams to be able to work together between themselves, particularly when it comes to basic things like safety. But we also want to help connect these students to university researchers and companies both in Canada and internationally so that they can work together and start developing both the skill sets and the practical technologies that will help them to really go a long way in this industry. As everybody knows, this has been a very strange year in a whole lot of ways. And COVID-19 has created a lot of challenges. The Spaceport America Cup last summer obviously got canceled. We weren't able to make a Launch Canada competition happen for the same reason. And things are still pretty uncertain for the months ahead right now. But over the summer, when we were faced with this, we wanted to try to find something that we could do to make sure that the students still have the opportunity to keep learning and maybe find some badly needed motivation throughout these difficult times. So we started a virtual lecture series. And we had a whole host of talks. Some of these were sort of fireside chats with key players in the industry internationally. We were able to get the likes of Peter Beck, the founder and CEO of Rocket Lab. We got Tom Mueller, the co-founder and original head of propulsion at SpaceX, who developed many of their rocket engines and built their propulsion group. We heard from former space shuttle astronaut Mike Mullane, who talked a lot about space safety and how important that is and how you go about doing it. We got Tori Bruno, the president and CEO of United Launch Alliance, among several others. And we also had a bunch of talks on more focused technical subjects, from basics of systems engineering to basics of rocket safety, pressure measurement, all kinds of things. So this was a very successful initiative, and there's been a lot of demand to keep going with this. So we've got more talks planned going forward. So we really want to use this to help to make sure that people still have the opportunity to get the education that they need. Then, of course, there is the Launch Canada competition itself, and this is going to be our signature event. We're currently hoping that we're going to be able to do this next summer. Obviously, still a lot of uncertainty with COVID, but this is what we're going to be pushing for as long as we can. And the initial inspiration for the competition was, of course, the Spaceport America Cup. But we wanted to put our own twist on that and not just make this sort of the Canadian version of the Spaceport America Cup. So we've actually got 3 categories currently within the competition. There's a beginner category, which looks a lot like the 10,000 foot category at IREC or the Spaceport America Cup, and that's designed to be an entry-level, accessible challenge for new teams that are just starting out. So they'll be launching to 10,000 feet altitude. They're allowed to use commercial off-the-shelf rocket motors. And we've got an added payload challenge to encourage them to think about not just the rocket, but what you can do with the rocket. But then we've got an advanced category as well. And we wanted to make this one very flexible so that students can choose whatever aspect of rocketry is really exciting to them and pursue it. Unlike the cup, we don't set a specific altitude for this challenge. We just say it's got to be greater than 15,000 feet. Otherwise, just go with the beginner challenge. But beyond that, we try to take more of a systems engineering approach to it. So we allow the teams to tell us what their rocket is going to do. What is the altitude you're targeting? And then, just like in industry, they'll be evaluated based on how successful they are at developing a vehicle that can meet those requirements that they've set. It's open to specifically hybrid or liquid propulsion. So that's the one key requirement for this challenge. You can't use an off-the-shelf motor. You've got to do it yourself. And teams are encouraged to work innovative technologies into their projects as well. But in addition to the 2 launch challenges, we've also got a technology development challenge. And that came about because we realize that there's a lot that goes into developing a rocket. And if you've got 1 year to build and launch an entire vehicle, that doesn't always give you a lot of time to really go in depth in any of the key technology areas that are so central to rocketry. So we wanted to have a separate challenge that allows teams to take almost more of a science fair type approach, so that if they want to focus on, developing and static firing a new engine, developing a super lightweight liquid oxygen valve or a new telemetry system or whatever, they can enter with those types of projects as well. But we want to also encourage them to think actively about what are the real technological challenges that face the industry, so that they are not just developing technology for the sake of the technology. They're thinking about the larger context into which it fits. And we want to get them to think a lot about the entrepreneurial aspect of this as well. Is there maybe a business case for this technology that they've developed? Could they start a company and sell this to launch vehicle startups around the world? So these are the kinds of things that we want to do, and we also are actively seeking partners who are interested in this, who want to maybe get on board and sponsor a very specific sub-challenge, and then see what a whole lot of very talented, motivated students can do with that. So hopefully that gives you a bit of a high-level overview of what's going on in Canada with all of this, and what we're trying to do with Launch Canada to pull that community together. So I guess in summary, student rocketry really is taking off, so to speak, around the world, and it's an incredibly powerful way for students to learn, because they get really excited about it and passionate about it, and it motivates them to really go that extra mile and learn what they need to be successful practical engineers. There's also this great innovation component to it, because a student rocket team has the ability to do things much more cheaply than a company could, and they can assume a lot more technical risk than a company ever could, because they're doing it primarily for the learning experience. So this is an amazing resource to tap into, both for technology development and for skills development. And it gives students a really valuable chance to close the gap between the theoretical and the practical side. A wise person once said that rocket science is actually pretty easy. It's rocket engineering that's hard. And the challenge has always been that most university programs tend to focus a lot on the theory, but not so much on the practice. And so closing that gap from the theoretical to the practical to learn how to actually develop and operate these systems is really important. And this is what student rocketry allows us to do. Rocketry is also an amazing opportunity for international collaboration, as certainly you all well know, and I think that's going to be increasingly important going forward, and that's certainly something that is really important to Launch Canada. And at the end of the day, these are real-world systems engineering projects. They're really complex. They're open-ended, just like the real thing. And I can't think of any project that gives students a more multidisciplinary taste of real-world advanced engineering than rocket projects. So this is a really exciting time. Thank you so much for having me. And if you've got any questions, I'd be happy to answer those.
Okay. Yes, we have a few questions, but before the questions and answers, I would like to thank you for your time, for your presence and acceptance of our invitation to give us this presentation. It's almost a lecture about the rocket student rocketry in North America and focusing in Canada. It was amazing, and I totally agree that the student rocket is taking off, but not. It is not taking off just in Canada, but I think in the whole world. We can see new initiatives on Africa also, and
Absolutely.
Asia, for example. And you said two things that for me was very important. Rocketry gives a chance to close the gap between theory and practice,
Yeah.
and it's a real systems engineering. So I totally agree with this, and I think with this kind of a research and development of rockets during the graduation or undergraduation time, students can get more involved with real applications. It's very nice. So I will pass the word to João. He has a few questions. So João, please.
So we have some questions here. First from LASC team, we were very pleased with the whole presentation. We liked a lot, and we could really see everything that you were talking on. They were things that we encountered on our way here while developing the Latin American Space Challenge. So you were talking about some challenges, and we faced those challenges as well. And from Gabriel here, he asked, on your point of view, what are the challenges of having liquid rockets on a student competition? What do you think about that?
With liquid rockets, I mean, the real challenge is the complexity. There are certainly great aspects to liquid rocketry. I might be a little bit biased as a liquid rocket person, but one of the nice things about them is, unlike with a solid rocket motor, you can literally test the very engine that you're going to fly. So it's possible, if you do it right, to have quite a safe, reliable system going into it. With a solid rocket, you're fundamentally facing a process engineering challenge to try to characterize your process and make sure that you can reliably make motors with it. The challenge with liquid rocketry is that obviously there's the cost. You just have a lot of high pressure fluid components, all of these things that can get expensive. And there's the complexity, because with the multiplicity of moving parts and components, that's more opportunities for things to fail, and that's more opportunities for things to interact in really strange ways, so that one failure leads to worse things happening. And one of the things that's really important when you're tackling something like this is to, go in with a little bit of humility and understand how much complexity there is, and be really creative about trying to figure out, what can go wrong, and be really rigorous about learning how to do this safely. Because like most things in engineering where there are hazards, there are also ways to work with those hazards. But you've got to know what those are and go in with your eyes wide open. And so that can be difficult for teams, and that's partly why Launch Canada is really focusing on the educational piece and making sure that student teams that want to do this can get connected to this larger community who can, take part in design reviews and make sure that they're not making any really glaring mistakes.
So yeah, it's all about community, right? And
Absolutely.
we have some other questions from Victor. He's asking how ITAR affects Canada initiatives on rocket launch. Do you have some problems with ITAR, or?
So ITAR is an interesting one. I mean, ITAR specifically applies to U.S. origin technology. Okay. So something that's developed in Canada is not ITAR by definition. Canada, like most countries, Canada has its own controlled goods and export regimes that have some similarities to ITAR, but it also has some differences. So generally, Canada is actually in a fairly strong position to work with the rest of the world. As a result of that, because ITAR does not apply directly to things that originate in Canada. It does mean that for Canadian citizens who might have that dream job of wanting to work at SpaceX, that can be really difficult because it's very hard for a non-US person to get hired at a US company that does rockets or space launch, which tends to mean that it's all the more important to try to make sure that people here have opportunities to stay here and do these things if that's what they want to do.
Okay, thank you very much. Those were very good words from hearing from you. Really into this business in Canada. So I don't think we have any more questions, right? Yeah, we are good to go with the questions. So thank you again, Adam, for your time. Thank you for being here and talking about Launch Canada. It's really awesome hearing from you everything you guys are planning to do. And we hope that LASC and Launch Canada can cooperate and do exactly like you said, be more like a community to propel rocketry towards a really great point where it can help a lot of teams worldwide to like really, as Calvin said and you said, apply the knowledge into their rockets and really make more practical things than just theoretical things. So yeah,
absolutely, I'd love to. Thanks so much for having me.
Thank you.
Hello, everyone. We are back with our 2020 Latin American Space Challenge conference, and now we will have Rasmus Pedersen from a Danstar. It's a rocketry group from Denmark. Uh, Rasmus also works in the booster division from the Copenhagen suborbitals, and he will give a presentation to us about Dragonfly, the bipropellant rocket that was launched at Euroc 2020. So, Rasmus, thank you so much for accepting our invitation, and we are very happy to have you here. So, thank you.
Thank you so much for the invitation. It's a real pleasure to be able to present our experience here at the Latin American Space Challenge.
Nice. Thank you so much. You can start. Thank you.
All right. So, contrary, kind of opposite to what you just heard from Adam Trumpur, I'm coming from the other side of the fence, so to speak. My name's Rasmus. I'm the project manager of the Dragonfly project, which has been Danstar's undertaking for the last few years, and I'll be telling you about the launch of the first European student researched and developed rocket, bi-liquid rocket at Euroc 2020. So I think it makes sense just in the beginning to go over what even is Danstar. So it is an abbreviation. It's short for Danish Student Association for Rocketry, and it was founded 4 years ago in 2016 with the original goal of launching a recoverable bi-liquid rocket. And that was it, no more, no less. Back in 2017, we started working on the Dragonfly project as kind of a small group, and we've since grown quite a bit into 5 different sub-teams, which are mechanical division, the electronics, the software, telemetry, and marketing. We have around 35 active members now, and that's approximately the same amount of people we had when we ended the Dragonfly project. So we're looking forward to starting the next project with approximately as many members. So the Dragonfly project was a development project of Danstar's first bi-liquid rocket, actually first rocket ever. And in developing the rocket, we also had to develop some key technologies in terms of launch infrastructure, because like I just said, this was Danstar's first project, so we didn't really have anything supporting the launch of a rocket of this complexity. So we also had to figure out how to do all of that from scratch, more or less. And in the beginning, our goal was actually to compete at the Spaceport America Cup in the 30,000 feet category, in the hybrid liquid category. And that then since changed. Our original goal was to compete this year in the competition, but unfortunately it got canceled due to COVID. So after it got canceled, we were, of course, very saddened because we were looking forward to launch. But of course, we completely understood the reason for the cancellation of the competition. Anyhow, we reached out to ESA and basically asked them why we didn't have a student rocketry competition here in Europe, because now we knew that a lot of European rocket teams actually were looking forward to launching at Spaceport America Cup. So quite a lot of these rocket teams within Europe had more or less launch-ready rockets that now didn't have a place to launch. So this was kind of the story that we gave to ESA, and they quickly got back to us and set us up with an organization called Portugal Space, who were looking to basically expand their network within student rocketry. So they saw this as a perfect opportunity to host a rocketry challenge in Europe, and together with Copenhagen Suborbitals and Propulse from NTNU in Norway, we laid the groundwork for this competition, where later on Copenhagen Suborbitals, Portugal Space, and some other organizations picked up on it and actually had it become a reality. And just for this year's instance of the competition, the rules were largely inspired by the Spaceport America Cup, of course, because all of this happened in a very narrow time frame. our contact to ESA happened back in February this year, more or less immediately after we heard that the Spaceport America Cup had been cancelled. So this entire undertaking of having this competition took less than a year, basically. So it's all very, very inspiring to be a part of. So again, just to give you some sense of scale, for the Dragonfly project, which is a biliquid project, it started formally back in September 2018, and it ended in this November here in 2020 with a debriefing meeting where we went through the technical details of launch. So when you do the subtraction, you end up with a project which lasted 2 years, 1 month, and 26 days. And doing the math, you quickly see that's quite a lot of time, and especially the hour mark is quite interesting. 19,000 hours spent on the project, and then divided that out or multiplied that out on all of the people working on the project. So quite obviously, it's a massive project, but yeah, we managed to go through with it. That's amazing. So just to give you an overview of the Dragonfly rocket, we'll start from the nose cone to the right. So in the nose cone, we have our recovery compartment, which has 2 parachutes, a drogue chute and a main chute. The drogue chute is to be deployed at apogee, and then the main chute is to be deployed at around 500 meters above ground level. Moving 1 step down, we have a boilerplate payload. We had to have this payload as a requirement from the rules at Spaceport America Cup, but we did not want to invest any time into developing an interesting payload because we were also developing this liquid rocket from scratch, and we prioritized the liquid rocket basically. So we just put in a dummy boilerplate payload that was just a 4 kilogram mass and no more than that. 1 step down, we have the avionics section. This is the smallest part of the rocket, but also one of the most important ones. This part of the rocket contains the engine controller and the telemetry units, and the power supply systems for the rest of the rocket. So this is what makes us able to actually control the rocket prior to launch and during flight receive telemetry data. Going another step down, we have a pressure feed system. So Dragonfly runs on a pressure fed cycle. So we need a high pressure system above the propellant tanks. And this is what you see here. It starts out at 300 bars. And by the end of flight, like when the tanks are depleted, it's around 50 bar lift in the system. Then we have a common bulkhead propellant tank. So the tank is actually 1 unit, but it has a dividing plate between the 2 volumes. So the oxidizer for the rocket is nitrous oxide, and the fuel is isopropyl alcohol, which are then divided into 2 compartments inside the tank, and then they have pass-through piping such that we can lead the pressure-end gas into 1 compartment, and then have a pass-through pipe for liquid for the other compartment, passing through each other, so to speak. It's a bit complicated. Then moving 1 step down, we have the liquid feed system. This is the part of the rocket that controls the flow of propellant into the engine. So here, the 2 most notable components are the main valves, the oxidizer and the fuel main valve. These are the 2 components that are responsible for engine startup and basically keeping the engine running. 1 more step down, we have a 3D printed, regeneratively cooled engine. So it's a stainless steel unit which has been 3D printed, and then it's kept cool by running the fuel, so the isopropyl alcohol, around a cooling jacket around the combustion chamber. So this is, of course, an undressed version of the rocket, so to speak. And when it's actually cladded, you can see this picture we took just immediately before putting it into the flight crate before leaving for Portugal. Here it doesn't have the fins mounted, but you get a sense of scale for the rocket. It's around 4.5 meters long, and the diameter is 18 centimeters. So it's quite big. And now to the actual launch. So I would like to say that it went smooth and we had no problems, but you can probably guess that this is not true. We actually had quite a lot of problems on launch. And among these, we saw an issue with the fueling system, which failed on the launch pad. We had an ignition error, meaning the rocket did not start, quite literally. And then after we eventually got the rocket launched, we had a deployment failure of the main parachute. So quite a lot of things went wrong, but since we had done so much testing and so much practice from home in for example, we did a vertical test. We did several vertical tests of the rocket on a static test bench just to get into the flow of fueling the rocket on the launch pad. We were quite confident in our ability to navigate around the failure in the fueling system, so we managed to circumvent this. The ignition system, we also found a solution for, and then the deployment of the main parachute. I guess I'll show you the aftermath by the end of this presentation. So the fueling system, which failed, I'll just briefly explain to you how the fueling system works. So at the bottom of the propellant tank, we have a check valve, and this is for the nitrous side. We have a check valve, which is a one-way valve. So this allows us to put liquid into the rocket, and it doesn't allow the liquid to go back out because it's a one-way valve, only goes one way, which is into the rocket. During fueling on the first attempt, this valve got stuck, basically. So it did not close, meaning that the liquid, which was supposed to stay inside the rocket, was able to squeeze through, and it wasn't fully open either. So all that happened was that we had a mist, like a small cloud, you can see in the picture, of nitrous oxide vapor, which was leaking out of the rocket. Luckily, this system, this error solved itself a few seconds after the decoupling of the fueling hose by the pressure inside the nitrous tank just pushing the one-way valve closed, which is how it's intended to work. But it didn't immediately happen like that. So this was another stress factor on the launch rail. Obviously, it's quite a lot of stress already launching a rocket that you spent the last 2 years working on, even though you've tested everything rigorously from home. So having this thrown into the mix was no pleasant experience, but we managed to navigate around it. Then the second error which hit after we thought we had solved the fueling error was an ignition system failure, which is quite crucial on a rocket that you want to launch. So what happened was that in our ignition circuitry, we have quite a lot of checks. So we have some AND gates, which are the logic that tells the actual ignition system to fire, which needs a high signal from the rocket and a high signal from mission control. If it does not get this, then the rocket won't launch. Now, at the launch site in Portugal, we had a electrical setup which looked like we had a generator at the launch rail, and then we had another generator at mission control. This caused a ground loop, which then fried this AND gate. So now this AND gate didn't work anymore, which meant that I don't remember which part of the AND gate worked, but basically when one side of the system, so that could be either the mission control or the rocket, sent the high signal, the AND gate would never open. So the final part of the ignition system would never receive a green flag to turn on the igniter. So the igniter never turned on. So this resulted in the rocket just spilling its fuels out on the area around the launch pad. And this is probably one of the worst feelings I think I've had in my life after traveling 3,000 kilometers from Denmark with around a metric ton, quite literally, of cargo, including the launch rail itself and our support equipment and the rocket too. Then seeing the rocket empty its propellants onto the floor on the launch pad was as brutal experience. So, but yeah, we basically had to scrub the first launch attempt, but we were granted very generously by the Portuguese authorities another launch window around an hour later. So we took it and we went through a bunch of checks on the rocket to make sure that actually it was ready to do another launch attempt. And this is one of the beauties of bi-liquid rockets, is that you can just refuel and try again if something doesn't work. So we did exactly that. However, now we only had enough nitrous oxide left for half a tank. So we could not fuel the rocket completely. Of course, we had enough fuel, but that doesn't matter if we don't have enough oxidizer. So we could not fuel the rocket completely, but we went with what we had, basically. And the ignition system, we hadn't really figured out what was wrong with it at this point. So instead, we chose to rely on some local pyrotechnicians that were present on site to aid some of the other teams, and our team included, with like off-the-shelf motors and also ignition devices like electrical matches, for example. And they actually had a remote control system which was completely decoupled from our system. So the way we coordinated this with them was that we would install one of their ignition systems inside our engine. And keep in mind, we'd never tested this because obviously we'd been using our own ignition system at home. But either way, we installed their ignition system inside our engine, and then we told them that, so when we do the countdown from 10, the terminal count, you press the ignition start at 7. So T minus 7 seconds. So this was very rudimentary, but again, we were at a point where we had to grasp for straws, more or less. So we took any chance we could, and we couldn't do much else than just say, all right, guys, this is one shot. The one shot we have left, so let's go, right? We just have to go for it. And it worked quite incredibly. So we had liftoff, and we saw a nice stability margin. This is based off of the data we extracted from the rocket after landing. So we saw a nice stability margin at departure. However, we only had half a tank, like what I mentioned. And during flight, we saw a maximum velocity of around 200 meters per second. That's around, I think it's 700 kilometers per hour. And then we saw an apogee of 2.2 kilometers. And I'm going to show you a video now. I don't think it has sound, but I'll show you a video now of the bottom-facing camera of the rocket. So we had a camera installed right next to the engine, which is looking down. So that's what I'm going to show you now. And now for the remainder of the video, the rocket is just falling down. There's not much to see except that it's spinning around. So let's just move on. So we could see that at apogee from the downwards facing camera that we had a nice drogue chute deployment. And then on the right, you'll see our upwards facing camera. Now, remember I told you that we had a main chute deployment problem. This is where that happens. So think about the fact that we are seeing the drogue chute, so the initial parachute in the downwards facing camera. This means that the rocket is heading one way and the parachute is in the other way. So now what happens is that the rocket is getting pulled around by the drogue chute. So the rocket suddenly makes a flip in the air. And this flip was enough to pull out the main parachute prematurely. This parachute was not secured mechanically. It was just held in there by the pressure of the deployment barrel, the deployment tube. And since we had not anticipated that this would happen, we didn't have enough force in holding in the main parachute. So the main parachute fell out prematurely. And that led to a partial deployment of the main parachute, but in such a way that we were not able, the rocket, when actually deploying the main parachute, could not salvage the deployment. So this is how it looked going down. We had a descent rate of around 30 meters per second. And you can see here on the picture that you have the pink main chute at top, on the top here, and it's kind of like all coiled up in a pile of cloth, basically. It's supposed, when it's actually deployed, it's supposed to have a diameter of around 4 meters. So it's supposed to be almost as wide as the rocket is long. And you can see here that is quite clearly not the case. So the main chute had entangled itself in all of its cords while it was falling from apogee, and this resulted in an impact of the rocket with the ground, where it saw a G load of in excess of 100 Gs. So the rocket took quite a beating on its landing, so to speak. So the liquid feed section, the section just above the engine but below the tank, now became an impromptu crumble zone, kind of like you have in Formula 1 cars with the nose of the car that's supposed to crumble to absorb energy in case of a crash. And overall, the rocket suffered lots of internal damages. The flight computer, which was situated right below the payload, had the payload crashing down on top of it. So you can see how destroyed the flight computer is on the picture here. But miraculously, when we had removed our power supply units from the power supply, which were the most destroyed because these were on top, we could actually power it up with a benchtop power supply and extract the data. So we ended up still getting full flight data from this, despite of the main chute deployment error, and that allowed us to do a full analysis of what had happened, which was incredible. So even though you might think that this is only a partial success, I would argue that given that this is the first European bi-liquid rocket developed by students ever to be launched, and the rocket came down in one piece, still slightly defect, but still one piece. This was an astounding success, and nothing short thereof. So I think I'll just end it on that note. And if you have any questions, I'd like to answer them. I have also pretty in-depth knowledge of some of the technical systems of the rocket, so anything can go. So just shoot me some questions and I'll answer. Thank you for listening, and thank you for the opportunity for even talking.
Thank you so much for your presentation. It was really nice to see a real application flying a liquid rocket be prop. It was amazing to see the flight and everything that you pointed out about the development and building the rocket. And also, I personally, I was very anxious and excited by your flight. And me and the PION and LASC team, we were talking almost every day about the rock. And if you could to see a live stream video or something like that, because we wanted to see the Dragonfly, and it is a great opportunity to have you presenting the launch here. And also I and all of our team, we would like to congratulate you and your team because of
Thank you
this success. It's not easy. It's very complex. It's rocket science, and you did an amazing job. So congratulations, and of course, thank you for participating in this live stream with us. So I will pass the word for João Pedro. He has some questions, and I think the questions it's going to be something very interesting for answers. And João, it's with you. Thank you.
Thank you so much for giving the opportunity even for Danstar to be able to present the launch here. It's a massive achievement. So thanks a lot.
It's really awesome to hear from you everything, and I personally appreciate the fact that you were so open about everything, because we think that this is really great to be able to, like Adam before said, to be in a community where everyone learns from the other, right? So you said some things like, oh, we had some trouble with our valves, so right now other teams, they can be something like, oh, I need to check my valves because the guys from Danstar had some problem with their valves, so I need to check mine, maybe triple check, quadruple check, or something like that. Or do a thing that we do around here, that is the buddy system, right? So we have a small question here. We'd like to know a brief answer from you on what it is the support from ESA like.
So actually, we were not in contact with ESA much at all. So the correspondence with ESA was more or less just me sending an email inquiring about a European rocketry challenge. And then immediately after that, we were set up to communicate with Portugal Space. So from a student point of view, that was all I saw from ESA. I'm quite sure they might have done a lot of stuff behind the scenes, which I don't know of. But from my point of view, that was all I saw.
Oh, okay. And from Bruno here from the LASC team, what kind of things you had to do to prepare a 3D printed liquid engine? Because we know you have to do some cleaning and some things like that. So what kind of works you have to put on?
So, okay, actually, thank you so much for that question, because I was on the engine design team, so I can answer this very well. So So we had a goal from the beginning, being that we don't want to do a lot of work on this engine when it comes out of the printer. Obviously, it still has to undergo heat treatment and some of these mechanical processes for it to be even like mechanically sound. But we had a criteria being that basically we should not touch it much. So all we did after it came off the printer was that we sanded down, literally with my hand, I sanded down some surfaces, which were for the O-rings, and then we tapped some holes for some screws.
Oh.
And that's it. And then we installed the injector and the oxdome and went testing.
Oh, so these other parts, they were machined, not 3D printed, right?
Yeah. So we had an injector and a top piece for the engine, which were machined in aluminum.
Okay. So I think that's it for questions from here. Let me check here on the YouTube stream.
Ask Victor Capassa.
I think I have a question from Victor that is here on the meet as well. So Victor, can you speak here?
Yeah, you mentioned something about a upcoming European Space Challenge, something about that. If you could say a few words about this upcoming event, this idea.
Yeah, so actually the first instance of this event was our launch among a few other teams who also launched. So this year, in this October, around a month ago actually, they had a pilot event, which was the European Rocketry Challenge, the first edition of it. So they're planning to repeat this indefinitely, I presume, kind of like Spaceport America Cup does. Every year, such that European teams no longer have to take the rockets to the US, which can, at least in our case, it would have been quite expensive, the shipping of our components, because we had to bring so much stuff, right? We had to bring our launch rail, we had to bring all our support equipment, so it's prohibitively expensive. But now with the competition in Europe, suddenly there's a window, there's an opportunity for European teams to enter the student rocketry scene at a much lower price point, because they don't have to go to the US anymore.
Perfect. Thank you.
Okay, thank you, Victor, for your question. So I think that's it. On behalf of LASC, I'd like to thank you for your time, Rasmus. It was really, really great hearing from a team. So as you said at the beginning, I thought that was very funny. On the other side of the fence, right? We heard from Adam, that is on the Launch Canada, and he was talking about the innovation and everything related to that. And then you came on and talked about what you and your team worked on for 2 years. So yeah, everyone, rocketry is really hard, and they worked really hard for 2 years to launch this rocket that was the first bipropellant liquid rocket from a student team in Europe. So that was really nice. It was really nice having you here, Erasmus. And
thank you so much.
Thank you for your time and your presentation here again.
Thank you.
Just a sec, Walter. Just a quick introduction. Hello, everyone. We are back after our break, and for this last part of the conference, we will have some podium sessions. We are going to start with the Team 3, Universidad de Baja California, UABC, from Mexico. And they will talk about their Club de Investigación Universitario de Desarrollo de Sistemas en Sistemas Espaciales. And we have here Walter. And Walter, thank you very much for your time and presenting the podium sessions. We are very excited to see the presentations, and for those who are watching us on YouTube, feel free to ask any questions. Walter, you have 10 minutes for presentation, and 5 minutes we are going to ask you some questions from the audience and from the LASC team, okay? So feel free to start when you are ready.
Thank you. We are the University Research Club for Space Systems Development, and our mission objective is going to be design, build, and test and fly a student design launch vehicle at a specified altitude. We are reaching to successfully transfer and deploy a 4-kilogram payload at Apogee. Also obtain an L3 certification with Triple Rocketry Association for 2 of our team members. The total length of a rocket is going to be 100 inches. It's going to have a diameter of 4.024 inches, a total weight of 16.7 kilograms, and estimated average stability takeoff of 3.92 col. We made a previous simulation of how everything's going to be assembled in a rocket, which is the payload, the avionics, the motor retainer, and we designed this rocket to carry a 4-kilogram payload at a minimum altitude of 3 kilometers. Based on our previous simulations that we started, and in these simulations, the smooth airflow around the lower fuselage makes a velocity distribution as calculated. Based on this, we decided to choose to buy a rocket kit as a starting point and adapt it to the needs of our mission. The rocket kit that we decided to purchase was the Matco Rocketry Model Rocket. The specifications of this rocket was similar to the ones that we designed on our previous simulations and on the programs. As you can see, we have a graphic of the thrust of how it's going to be how it's going to be during flight. And we decided to, during our investigation, we started doing our previous calculation for drift calculations, which we made an average of from 0 miles per hour to 20 miles per hour. And we do the hand calculus drift, and we compare it to the simulations on open rocket drift. Then we, based on the distribution, we did a graphic design of the drift, how it's going to be working during flight. And we also did one for the stability. This is the study that we do it for the stability from ignition to motor burnout. And we decided these are one of the basic components that we use for a rocket. We decided for a drop parachute of 24 inches with a drag coefficient of 1.5 to 1.6. And our main parachute is going to be for 96 inches with a drag coefficient of 2.2. Yes, we decided to put 2 altimeters just in case that either one of them doesn't work. We have a backup for them. And as you can, we deploy our schematics of our circuit for the altimeters. that will be all for us. Thank you so much for your attention.
Okay, Walter. Thank you very much for the presentations. We have a few more minutes for questions and answers. We have some questions from the audience, and I would like to ask the LASC organization team would like to ask you some questions. First one regarding how the COVID-19 pandemic affected the activities on the university in Mexico, especially on this rocket trial perspective on your team, and how it's going on today.
During the first months, we decided to organize ourselves so that we can still be working on this project. And as well, we started doing meetings like this one, and we started to be planting ideas. And either one of our team members started to be displaying their own ideas, and then we started to work together on the ones that we decided were going to be the better for us to work on this moment.
Oh, understood. Perfect. And we have another question from Mateus. He's asking about how is the partnership between Universidad Autónoma de Baja California with the Mexican Space Agency, the AEM, that we know that the AEM is doing a lot of new activities, launched some small satellites together with some universities, and we would like to know if the Mexican Space Agency has some partnerships with the rocket teams, if they are promoting, and how is working.
We're working with them continuously, and we're in constant communication with each other, because we're also trying to start with new projects. We're participating in Spaceport, and we're also participating with the certification of Tripoli with them.
Oh, great. So just 1 second, I'm gonna check if there's any other questions from the audience. Okay, and we have another question now from Victor. He's asking about if your team has any vision to build, develop, and launch a rocket to exceed 100,000 feet above ground level altitude. So, are you guys working or visioning to make a project like this?
Yes, we're actually working with members of Tripoli, and that's gonna be like our main mission. Right here, we're focusing right here. These are like our trials to keep improving to finally reach 100,000 feet.
Oh, great! And you have a schedule for it? Are you planning to have it on like a 2022, 2021? And how is the progress together?
In 1 year and a half.
1 year and a half. Okay, perfect. Great. I don't think we have any more question, Walter. Thank you very much for your presentation. We really like it, and thanks also for your time answering our questions. I'm sure that the people who are watching us liked a lot of your presentations, and thank you very much.
Thank you so much for your time.
And we are back. Hello, everyone, again. Now we have another podium session for Team 26 from Minerva, UFRJ. They are from Rio de Janeiro, and they will talk about Monte Carlo analysis, coupled hybrid rocket motor internal ballistics. This is a very interesting theme and topic. Here in Brazil, we have a lot of teams, a lot of institutions, a lot of companies working on hybrid rocket motors, and this kind of studies is very important. And we have here Igor. Igor will talk more about it. Igor, you have 10 minutes, and after 10 minutes, we will have 5 minutes for a question from our audience and from our LASC organizational team. So, Igor, as soon as you get ready, feel free to start your presentation, and thank you very much for having you here.
Okay, thank you, Yamato. So I'm Igor, I'm the project manager at Minerva Rockets, and today I'll be doing the presentation on Monte Carlo analysis of hybrid rocket motors. So overview of the presentation. I'll do an introduction of hybrid rocket motors, the motivation and the scope of this project, as well as explain the hybrid rocket motor internal ballistics model that we'll be using, and the Monte Carlo analysis as a final. So first of all, it's important to define what is a hybrid rocket motor, and it's defined by having the oxidizer and fuel in different states. In this case, we'll be dealing with liquid oxidizer and a solid fuel grain. The motivation of this work is institutional, as in developing hybrid rotor technology at UFRJ, and it's technical, as in developing a tool to model the behavior of a hybrid propulsion system, such as we have for solid propulsion systems in open motor or burn sim. And after developing this model, do a statistical analysis to define the operational envelope of the system. The scope of this project involves a one-dimensional transit simulation, where the pre- and post-combustion chambers are not modeled, and the fuel rate is considered constant alongside all of the grain, and we have instant ignition on all grain surfaces at time 0. First of all, in the hybrid rocket internal ballistics model is the tank blow-down model, where the self-pressurized nitrous oxide is depleted into the tank, into the combustion chamber. We model that in a two-phase and one-phase oxidizer, and for the vapor phase, we utilize the real gas equations to better model the system. For the solid fuel grain, we have simple geometric relations to define the burn area for the base grain, and the code is also capable of modeling the phenocyle and star core geometries using the far-smarting method. Another thing of note is the burn rate that is defined by the oxidizer mass flux and the constants A and N for burn rate. This does not have any pressure correction factors or grain length correction factors. So it's a simple burn rate equation. For the combustion modeling, we use the CNASA to get tables of interpolation based on the oxidizer to fuel ratio and pressure to get the adiabatic flame temperature, rate of specific heats, and the molecular weight of the combustion product for each time step. Combining all of those models, we have a deterministic approach to hybrid rocket modeling, where it gets 3 kinds of outputs: a graphical output, as shown in the pictures below, an output text file with the time-independent variables, such as specific impulse, total impulse, mean chamber pressure, and etc., and an output table with all of the parameters varying with time, such as thrust, pressure, oxidizer to fuel ratio, all of them varying with time. Having this model, we can treat it as a black box and do a Monte Carlo analysis so that we can translate our uncertainties on the inputs into uncertainties of the outputs. And for that, we chose the Chimera test motor as a base. That is a motor that is being in development by Minerva Rockets. And we run 5,000 simulations to analyze this for this study. On the right, there is a table with some parameters of the rocket motor. And now we model each of those parameters as a normal distribution with a given standard deviation. Not all of those parameters may vary with a normal distribution, but for this first study, this was the case. Running the analysis, we got a series of histograms defining some properties. Those are the time-independent properties like total impulse and peak chamber pressure, and they closely resemble the normal distribution. The same thing happens to the peak thrust and liquid mean thrust, mean thrust in the liquid phase, that closely resembles the normal distribution with a given standard deviation. But some other parameters that are more complex, such as the specific impulse, doesn't resemble the normal distribution, are more closely related to the inverse Gaussian distribution or to the F distribution. But for this preliminary analysis, they were considered as having a mean and a standard deviation like a normal distribution would. After combining the input and output data, we could also get the heat map of the correlation between each parameter. This is probably the most important result of this analysis because as Minerva doesn't have an experimental motor to get an empirical intuition of how each parameter correlates with another one, this table really shows which input is really responsible for which output, and can really help us in the design phase to create a rocket with a better performance. Now, for the time-dependent variables, we decided to calculate a mean value and a standard deviation for each time step, and plot the mean value together with a 3 sigma heat map in a graph such as this one you see of thrust over time. We also plotted tank pressure over time and chamber pressure over time, and we got a noise in the tail-off pressure. That's probably because of the difference in time duration of each simulation. So in the end, when you have very few simulations that reach this time, you really generate some noise that influences the graph. But for the linear regions and the exponential decay, we have a lot of data, and we can trust these plots. Something that we noticed is that our initial estimates of standard deviation for the input parameters were quite high, especially in the burn rate constants, because we don't have experimental data of burn rate. So we had to do a fixed, a relative uncertainty that led to a really high burn rate deviation and OF deviation. You probably noticed the peaks in chamber pressure, thrust, and tank pressure. Those peaks are not generated by peaks in pressure as it is, but actually from the peak and the uncertainty on this region of decay. Because when you have the change on oxidizer phase, you have this drop in chamber pressure and generates this really big gap between simulations, which leads to a high standard deviation that generate those fake peaks. But those graphs are still valid and are a really good representation on the linear regions and the linear region of the graph. The conclusions of the study that this methodology is capable of calculating the operational envelope of a hybrid rocket system, and it also helped us a lot to better understand the relationships between the inputs, parameters, and how these affect the systems as a whole. For follow-on work, we need validation of our ballistics model, and that's done by static firings. And when we have enough static firings, we'll be able to also validate our Monte Carlo analysis. We are also looking for groups to share experimental hybrid rocket data so that we can cross-validate our results with them. On the software development, we want to integrate this workflow into a flight simulation tool to analyze the complete statistical envelope of the rocket plus hybrid rocket motor system. And we're also planning on releasing the source code for open development to the community. Unfortunately, that was not possible to do today, but soon we'll be releasing the source code on Minerva's Rocket GitHub. That's it for this presentation. Thank you for listening, and do you have any questions?
Okay, Igor, thank you very much for your presentation. It was really good. We from the LASC team liked a lot. It's such a nice and great work. As you say that at the end, this kind of study will be is essential, and with this kind of data, you can have more precise simulations with more precision data. And we have a few questions from the LASC team. The first one is about the oxidizer fuel rate that you are analyzing. In your analysis, are you considering also some other constraints other than performance, like financial, and how like costs of the oxidizer, cost of the fuel, and how it affects on the final system, or it's based for now only on performance?
Yeah, for now it's only on performance, but it's a really good that's a really good suggestion of adding also the cost. We could plot a 3 sigma cost value. That would be nice.
Yeah. Especially down here in Brazil, we have we all know the oxidizer price, especially from nitrous oxide and other kind of oxidizer can be very expensive down here. And another question is about the experimental data, and how you guys are planning to get these ballistic coefficients, like the regression rate coefficient, the A, and the max flux exponential, the N. Are you guys trying to have a bench test developed by your team to get this data, a model only for that? And from the studies that you made, do you think you have a big difference between the theoretical one and the practical one? Because a lot of factors involved, like machining and finishing, and as you said, probably is inside this 3 sigma probabilistic. But how you guys are planning to get this experimental data?
Yeah, so there is a project in development at UFRJ to do the test bench motor, so that we could really get the parameters. And even this Monte Carlo analysis could probably help us a lot on narrowing down into the correct coefficients by seeing if, by running a series of analyses of a series of burn rates and comparing the data. But yeah, we are currently developing the test bench mostly for this purpose of getting the coefficients.
Okay, perfect. Let me see if we have any other questions from the audience. Okay, Igor, we don't have any other questions. Just a few more words. I think you guys are on the right way. We are seeing more and more this digital mission engineering world, where we have the digital model of the system. So more and more we are having this twin between the real world and the digital world to have more cost effective and more performance on our prototype, our final project. So I think you guys are on the right way, and thank you very much, Igor, for your time, for the presentation, and I would like to congratulate you and all the team that did this amazing work. Okay,
thank you very much.
Hello, everyone. We are back with the 2020 Latin American Space Challenge Conference. We are having our podium session, and now I will ask for the team 17, Projeto Júpiter, to present their podium session presentation. They will talk about design, testing, and analysis of a recovery system. So, Projeto Júpiter, you will have 10 minutes. So, good luck and thank you for all effort. So, you can start.
Thank you. Hello, my name is Gustavo. I've been part of the recovery team for 3 years now. And with the help of Leonardo, I'm going to present this podium session about design, testing, and analysis of a recovery system. Basically, we'll focus on the trustworthy foundation for the recovery systems we've developed during the last couple years. So I'll start by talking about parachutes, and later Leonardo is going to talk about the ejection system and the locking mechanism. As you might know, it is important to choose the best parachute option for each application. For this, many variables, such as the oscillation range and the CG, which is the drag coefficient, should be taken into account. However, although there are many references that present these values for each model, they don't show how to produce all of them. In particular, we had to develop a GAR flattening method to produce the GARs of the quarter spherical and the toroidal ones. So I'm going to explain this method for the quarter spherical. The quarter spherical is basically a parachute that has the axis relation as shown here. So from the diameter, we find the parametrization in function of theta and phi. For the flattening, we are going to work with only half a GAR. So we are basically using theta equals 0 degrees as a reference angle, which would be the symmetry line of the GAR, and theta as the half GAR angle, which would be the edge of the GAR. We are then working with only half a GAR, and the other ones gotten by symmetry. Now we have to flatten the figure, which is the most relevant part. So for the y GAR coordinate, we are calculating the distance between consecutive phi coordinates. These are the red lines. However, we have to add that to the sum of the already calculated distances. So for each phi, we are adding the red lines to the previous y coordinates. For the x coordinates, we are calculating the arc length for the equivalent curve level defined by each phi. These would be the blue lines. We are also adding to that 2 extra centimeters for sewing on each side. It is worth mentioning that the GAR area we obtained had only a small 0.2% area distortion. So after you produce the parachutes, you have to test them so that you know if the CG and the other parameters are what you expected. Basically, you have to validate them. There are then 3 test types. The first one is the wind tunnel test. You can see here that the drag measure is almost constant, which is advantageous. However, we've been only able to test small parachutes because the wind tunnel was small. Then there is the car test, which is the simplest to do, but the most difficult to analyze. For instance, we have to correct the CG as to consider the for-body wake effect, and we have to try to keep the car at a constant speed. Finally, there is a drop test. Here, we are basically getting data from the rocket flight. It offers real results, but they are more difficult to do. That's what we've done so far. However, we wanted to improve these tests. For example, the car test could be improved by measuring the wind speed as to normalize the force, since the car and the wind speeds are not constant. Another improvement would be to increase the height of the parachute attachment point to the car so that the parachutes aren't damaged. Finally, for the flight test, it would be interesting to measure the drag force over time using a load cell. Here we have 3 different CGs we've gotten for the same parachute. These 2 were measured in a car test, and this one through a flight at Spaceport America Cup last year. We can see that the real value is in between the ones obtained from the test. So it basically says that we can use these values. It's not going to give us the best approximation, but if we use the mean CG, we are having good results. Now Leonardo is going to talk about the other systems.
Hi everyone, I'm Leonardo, and as Gustavo said, I'm going to continue our recovery system explanation. So here you can see our deployment sequence. It is as shown. First the riser, then the suspension lines, and lastly the canopy. It was chosen to be this way in order to avoid the canopy force ejection, lowering both the failure risk and the snatch forces. It could damage the model or the parachute itself. Now, talking about the deployment power source, it is a CO2-powered ejection system, and I'm going to detail each main component and how it was its development process. Starting with the CO2 cartridge. We just buy sealed cartridges with different loads of gas, from 16 to 60 grams, and we choose their masses based on the weight it should eject as to ensure the deployment. Then there is the main tube. Its function is basically to contain and drive correctly the sharp piece to the seal. It should also let the gas escape through the holes on its sides, pressurizing the recovery model and opening it. Then we have the black powder chamber. It goes on the bottom of the tube with a small black powder charge inside. Also, there is an e-match that passes through the chamber, and when this match is activated, the sharp piece, which we are going to talk in sequence, is pushed forward, starting the ejection process. Finally, there is the sharp piece. It is positioned in the middle of the tube, being responsible for piercing the seal, which keeps the cartridge closed. As said, this happens as a consequence of the black powder explosion. Dimensioning our system was a big challenge. For it, we had to overcome some issues, such as the first one being able to know the exact amount of black powder for the system to work. The second was to avoid the sharp piece from getting stuck on the cartridge after breaking its seal. And the third and last one was to avoid an accidental activation by making sure the sharp piece was able to slide inside the tube on when we desired it. And we had to make several design and sizing iterations, and this added to the tests allowed for the optimal system we have today. For example, the geometry of the piece changed, and we added an O-ring around it, as shown in the slide. Here you can see how all the previous mentioned parts are assembled together. Inside the rocket, there is a pair of these, ensuring redundancy and increasing the reliability. Now talking about our system best qualities. First, it is a really safe one. Having such a small amount of black powder, which is about 1 gram, prevents the operator from being at risk during the assembly process. Additionally, the released CO2 counteracts the heat gases from the black powder explosion, minimizing any damage risk to the parachute. We believe this is our biggest differential from ordinary pyrotechnic ejection. Furthermore, as already pointed, it has been tested in many conditions, allowing us to be confident of its functionality. Also, the system assembly is very straightforward and can be done in less than 7 minutes, which is positive in pre-launch scenarios. Lastly, adapting our system to the new deployment masses is very simple. You just need to test it with the different CO2 cartridge sizes to find the most suitable one. On the next slide, we can see one of our empirical tests. It was a preliminary one for the SA Cup. On the occasion, it was a 3 kilograms mass that was ejected with two 32-gram cartridges. According to the next criterion, a successful ejection needs to push away the deployable at least 6 times the rocket's diameter. And for example, as a conclusion for this test, we needed a bigger amount of CO2 gas. Finally, talking about the lock-in mechanism. It is a simple one, but yet efficient on its purpose. As shown in the figure, it consists of 7 paracord core yarns braided together and tied to the U-bolts at both model ends. These yarns also pass through 2 redundant adapted black powder chambers, responsible for burning the yarns when activated, unlocking the model. On the left, you can see a tensile test we performed with these yarns. It shows that the lines can withstand about 1300 newtons before breaking, more than enough to ensure its security if compared to in-flight applied forces on our current rockets, which is about 300 newtons. And with all this knowledge we developed so far and settled, some new doors were opened for us. Now we are working on adapting our lock cutter to a reefing cutter and also developing a reefing parachute itself. So that was it. We would like to thank you all of you for your attention, and now we are open to questions.
Okay, thank you so much, Leonardo, Gustavo, and Isabella. This was a great presentation and a great work that you did. And I have a question. The question is about the really. Sorry, my tongue is being being hard. So reliability of the system. Okay, I want to know if you already have any calculation about the reliability, or if it's something that you are planning to do in the future. So I want to hear about it.
We believe that after dimensioning the CO2 cartridge properly, it is almost certain that it will be reliable during any flight. From our tests, after ensuring the CO2 gas mass is correct, we never had any problems with the ejection. But the process to get to the right CO2 mass is what can cause some risk to the ejection. So if the proper test is made, we can ensure it with over 95% success ratio. Calvin, sorry, you're muted.
Oh yeah, sorry, I was muted. Let me see. Thank you for your answer. It was amazing to know about this data. So I'm going to ask if there are any other question from the LASC organization and also from YouTube. Let me see. So yes, we have one question. Let me get this question. I just want a help here from my friends because I'm not. Yes, you can say it, John. It's going to help me.
Are you thinking in not using pyro components in the ejection systems?
Sorry, I couldn't hear it. Oh, okay. So we already tried to have a completely mechanical deployment, but we couldn't develop it so far. So we still use the small black powder amount. But surely a non-pyrotechnic ejection would be much better uh, in the sense of keeping the parachute safe before the ejection and during the flight. And we are working on it.
Okay.
Okay, nice. I think we do not have any other question. Your presentation was very nice and straightforward. So thank you so much, Leonardo, Gustavo. Is a is an all Projeto Júpiter team. The presentation was great, and I really want to see your work also in the challenge that we will have tomorrow. So thank you so much. We will have a just 1 to 2 minute break, and we'll come back with Topos 10. Okay, thank you so much.
Okay.
Okay, hello everyone. The last but not least pódio session. Now we have team 14, Topos, Projetos Aeroespaciais, and Pedro from Topos will talk about drag and stability optimization algorithm for trapezoidal fin geometries. So we are very excited to see the presentations. Pedro, you have 10 minutes of presentation and 5 minutes of questions. If anyone would like to ask something or any question, please feel free to use the YouTube chat. And okay, Pedro, feel free to start. You have the word.
Thank you. Hello, I'm Pedro Fontana, and this is the Team 14 technical presentation to the 2020 Latin American Space Challenge. Today, I'm going to present the drag and stability optimization algorithm for trapezoidal fins geometries. The fins are components that are responsible for the rocket stability, implying that they are extremely important to the mission's success and safety, but they also increase the drag force or may provide overstability, decrease the efficiency of the vehicle. Therefore, in order to find the most optimized fin design to be used in the coming mission, the new 1 kilometer apogee rocket of the group Topos, an algorithm script was developed and implemented using MATLAB that evaluates different parameters and utilizes them to choose the best trapezoidal fin geometry. Also, another objective of this script is that it can be used in any similar rocket project made by the team in the future, not only the coming mission, in a quick way as a designing tool. So the algorithm utilizes 3 analyses for the optimization process: static stability, drag coefficient, and dynamic stability analysis, and a 4th analysis to give enough data to softwares that test if the fin will be strictly safe during the flight or not, the lift distribution analysis. The process begins with a big number of fins being generated using the input data. All these fins have dimensions values, that is, root chords, tip chords, span, and sweep angle, contained in the interval defined by the user. This group of fins is reduced as the algorithm runs the first 3 processes, until it is reduced to the number of optimized geometries defined by the user. The first analysis performed by the algorithm is the calculation of the static margin, evaluating the vehicle's static stability. This may be useful to determine if the rocket has a tendency or not to return to its initial condition given an external perturbation like a wind gust, but this analysis will not provide any other information about the trajectory experienced by the vehicle, implying that it cannot be used directly in the optimization problem. But since one of the algorithm goals is to reduce the time to run the simulations, this analysis will be used as a filter for fins geometries before going through the next and more complex ones. This analysis evaluates the static margin of each fin generated by the algorithm using the following equation, where d is the airframe maximum diameter, xg is the position of the vehicle center of gravity, and xp is the position of the center of pressure. The values of the diameter and xg are easily given by the project. But as for the center of pressure, since the most critical moment during the flight regarding the vehicle's stability is the launch rail departure, and at this moment the rocket has a speed inferior to Mach 0.3, it is unnecessary to consider the effects of compressibility in the airflow. Therefore, using the Bernoulli's equation to calculate the position of the center of pressure guarantees a result with high precision and low computational cost. Also, the effects of higher angle of attacks in the position of the center of pressure are neglected, since it requires a more complex model, and the maximum angle of attack faced by the rocket in this moment is close to 0 due to the high speed of the vehicle. These are the Bernoulli equations applied in this analysis. And here it is shown the procedure to select the fins, where the red lines are the desirable interval of the static margin defined by the user, and the blue points are the value of this parameter calculated to each fin generated. The second analysis uses the United States Air Force Stability and Control.com method to calculate the fins drag coefficient. Since the maximum dynamic pressure experienced by the vehicle occurs approximately when it reaches the maximum velocity, this analysis will only calculate and optimize the drag coefficient at this moment, implying that the maximum drag force faced by the rocket will be minimized. This method divides the drag coefficient into 4 traps of drag: body drag, base drag, fin drag, and interference drag. But as the first and the second ones have no influence of the fins, it is not necessary to calculate these two parameters, since the result will always be the same no matter which fins geometry is being used. Therefore, this analysis will determine only the fin drag and the interference drag. Besides of evaluating an essential parameter to select the fins geometries, this analysis also has its own optimization process that, although being more simple than the final process, it is extremely useful to decrease the total script runtime. It consists in selecting a percentage of fins from the group submitted to this analysis with lower drag coefficient, being this percent defined by the user. The third process, the dynamic stability analysis, evaluates the vehicle's behavior during the flight when subjected to an index velocity at the moment it leaves the launch rail. This analysis tests a big number of things and has a higher computational cost and complexity than the others, which implies that the physical model used in it must be simple and, at the same time, accurate. For this, a 1 degree of freedom analysis is utilized to determine the rocket's angle of attack during the flight, using the Newton's second law for rotations, the aerodynamic damping moment, the jet damping moment, and the aerodynamic pitching moment. The aerodynamic pitching damping is caused due to the different angles of attack that components that generate lift, like the fins or the nose cone, are submitted when the vehicle rotates in pitch. As for the jet damping, it is generated due to the conservation of the angular momentum during the motor burning, also when the vehicle rotates in pitch. These are the moments utilizing this analysis. Most of the parameters used to evaluate the angle of attack behavior are not constant values during the flight, due to the rocket's propulsion that ejects the mass from the nozzle. Some assumptions that simplifies these parameters functions are utilized to reduce the computational cost, such as linearizing the CG position and the moment of inertia, interpolating the vehicle's speed over time using splines, and considering that the center of pressure position is constant. Although the simplifying hypothesis adopted, the equation is still a non-linear second-order differential ordinary equation, and due to the complexity of solving it, a numeric method is utilized to obtain the angle of attack over time, the Runge-Kutta fourth-order method. Therefore, after obtaining the curve of the angle of attack versus time, it is possible to calculate the oscillation frequency and the damping ratio of the vehicle. The average frequency is obtained simply by measuring the time between the first and last peaks, divided by the number of oscillations, and getting the inverse of this result. The damping ratio is calculated utilizing the logarithm decremented method, as shown in this slide. After the oscillation frequency, the damping ratio, and the drag coefficient from process 2 are calculated for each fin that passes from the first and second analysis, the algorithm uses the stored data of these parameters to select the best fin geometry. The objective of this optimization process is to minimize the drag coefficient, guaranteeing a higher vehicle's efficiency, to minimize the frequency oscillation, implying a less erratic trajectory, and maximize the damping ratio as close to 1 as possible, to reduce the amplitude of oscillation over time. The final optimization process consists of calculating a cost function involving these 3 parameters and selecting the fin that minimizes it. After the best fin geometry is selected, it is necessary to determine how the lift force will be distributed on the fin surface to assure its structural integrity. In order to find this, since the rocket will be exposed to different situations during the flight, this analysis uses the worst scenario possible, maximal vehicle velocity and maximum angle of attack. Although this scenario probably won't happen during the flight, this will give us a good security margin to the structural analysis. Since the fin is a flat surface, it is necessary to calculate the lift distribution along the fin chords and the fin span. Therefore, 2 different methods are utilized to determine it in each direction. The first one, the shrink method, uses the following equation to describe how the lift force derivative varies with the fin span. After calculating the lift distribution along the fin span, it is necessary to calculate it along the fin chord. The method used for this analysis is the approximation to a trapezoidal distribution, which assumes that the lift force is constant from the leading edge to 15% of the chord, and after this point, it decreases linearly to the trailing edge, where its value is 0. The total lift distribution in the optimized fin is calculated by combining the results from both methods, giving an accurate result of the load that the fin will be submitted during the flight. Here are the results obtained from the algorithm when applied to the Camera mission rocket. Here are the selected fin relevant data. Here are the static stability analysis results. Here are the drag coefficient analysis results. Here, the angle of attack and the angular velocity of the rocket over time using the select fin. Here, the final optimization process. And here, a heat map of the lift force acting in the fin surface. Thank you for watching.
Okay, thank you, Pedro. Great presentation. It's a really great study. We have a few questions. The first one, I would like to ask you what are the next steps from this study. Are you guys planning to have some experimental data as well, or what are the next steps?
So hello, I'm Augusto. I'm here. I'm also part of Topos. So yeah, we are planning to make some to check if our code is right. We already checked it using OpenRocket, which is a great program, widely used on the rocket world. And but yeah, we are planning to validate our code using wind tunnels that we have at the campus in which we study. Hopefully we'll be able to do that next year when this whole COVID situation ends. So yeah, we're definitely aiming to do that.
Okay, great. Thank you, Pedro, for the presentation. Augusto as well. Thank you very much for your time. We are glad to have you here presenting this. Let me see if you have any other questions from the audience or from the LASC team. Okay, no additional question from the audience. So we have a lot of people saying that the presentation was really nice. They like the slide and the content as well. So I think it's that. Thank you very much, Pedro, again, and Augusto, and Artur, and the entire TOPS team. And we are very excited to see your presentation, and I think the people that were watching us liked it a lot. So as Calvin said on the past, on Sunday, tomorrow night, we will announce the winners for each category. And thank you very much.
Thank you.
Hey, hello everyone. We are back with the 2020 Latin American Space Challenge Conference. We are ending the first day of the conference with a great presentation of Ricardo Freire. Ricardo is a Brazilian. He is a master's in space engineering by he will talk more about his degree. I forgot the name, but
University of Rome.
yes, thank you so much. But the main detail is that Ricardo will talk about satellite operations and the Brazilian Space Operations Center. It's something very interesting because mainly Ricardo has, I think he has the control over our geostationary satellite, the SGDC. So this is going to be a nice presentation. So Ricardo, thank you so much for your time, for your presentation. Thank you for accepting our invitation.
Hello, Calvin. Hello, everyone. So it's a pleasure for me to stay here and talk a little bit more about satellites and my job. And all the conference is awesome. So congratulations to you and all your team.
Thank you. Have a nice presentation.
Okay, so let's start. So as Calvin said, my name is Ricardo. I am an aerospace engineer. I work at the Brazilian Space Operations Center. There, I am part of the flight dynamics team, and we perform station keeping maneuvers and collision avoidance maneuver. In addition, I'm worked as a project manager in several projects of the Brazilian Air Force. And today, I will talk a little bit about satellite operations and the Brazilian Space Operations Center. So let's begin. All right, so the Brazilian Air Force has a lot of different commands, and one of them is the Brazilian Aerospace Operations Command. So the Brazilian Aerospace Operations Command is, of course, a Brazilian Air Force organization, and here there's a brief description of this command, which is a joint operation command permanently activated and responsible for the planning, coordination, execution, and control of aerospace operations, both recurring and occasional. So this is a brief description of this command. It is available online in public domain, of course. Clearly, I am not authorized to bring here classified information, so everything that I will say here is available online. But of course, that I will talk a little bit about satellite operations based on my own personal experience. And the Brazilian Aerospace Operations Command has different centers as part of it. And one of these centers is the Brazilian Space Operations Center, called COPE. So the Brazilian Space Operations Center, COPE, was built as a partnership between Telebras and the Ministry of Defense, the Brazilian Ministry of Defense. And there we operate and monitor the geostationary defense and strategic communication satellites, the SGDC, as Colin said. And the satellite has a dual application, a civil and military one. So using Ka band, we are able to broadcast connection in all Brazilian territory. And using X-band, we are able to process information related to defense and government areas. So here is a picture of the facility, the Brazilian Space Operations Center, here in the right bottom. And yeah, this is a pretty amazing and incredible building with a very beautiful architecture. And it is not only beautiful, of course. This building has a Tier 4 certification, so it's one of the most and the highest level of technology that we have. If you look close, you see that the build
We are having some trouble with Ricardo Freire feed and presentation. We will resume shortly.
apresentar agora. Vai lá.
Okay, guys, we are back with Ricardo. Ricardo established his connection. Everything is okay now. So let's get back to Ricardo's presentation. So Ricardo, the word's yours. So go on. Thank you.
All right, so I'm really sorry about that. So let's try to keep on this. All right, so I talked about the Brazilian Space Operations Center. I talked about the facilities, and here we have the satellite antenna that we use to perform the telecommand and telemetry receiving of our satellites. And here's the building. I said that the architecture of the building is in a format of a satellite. So we have 2 solar panels here and the satellite body here. So it's a very impressive facility. And we have a backup facility in Rio de Janeiro, which is a replica of one of these buildings here. And of course, to keep our operation working every time. All right, so I will talk a little bit about space operations. And I will start here talking in a general way, then we are moving on. So when we talk about satellite operations, we must have a 24-hour, 7 days per week activity, so we never stop. And we have 3 main segments. We have the space, the ground, and the users. And of course, we must guarantee a high reliability and availability of our system and of our operation. And to guarantee this, we usually use redundant equipment and systems. So here there's an image representing all these operations. So we have the antennas to receive and to send telecommand. We have the satellite control building. Usually, as we have here in Brazil, we would have 2 facilities, 3, and of course we must have communications between them. And we have the satellites, of course, the space system, and the users. And all of these segments are in a communication between them. So about the ground segment. So I will go further here about the ground segment, which is one of the parts which is most related to what I do, to my job. And I will talk about some basic elements and people who work in a space operations center. So the ground segment is one critical element in satellite operations. And you may not believe, but sometimes it's neglected in satellite projects because it's very common. We spend a lot of time and we spend a lot of efforts thinking about the space segment. But we sometimes forget that if we do not have a very good and reliable ground segment, we will not be able to operate the space segment. So the ground segment is a very important part. And we have a lot of elements to guarantee that the ground segment will work properly. So we have the ground communication network, which is part of the computers and the storage and all the communication between them. And so it's something very important. If something of these ground communications fail, we will have a real and bad problem. We have the RF equipment, the radio frequency equipment. So we have antennas. When we're talking about satellites, we must have antennas. There's no other way to communicate to them, no matter the satellite application. So we must have antennas, we must have amplifiers, and here we have some equipments that are really important in the ground segment. And let's talk about some people who work in the satellite space operation. So we have the satellite engineer, which is one of the most important engineers because the satellite engineer stay all the time following what is happening with the satellite, checking all the subsystems, and the satellite engineer knows a lot of all the subsystems of the satellite. But when something happened with a specific subsystem, there's a moment that the satellite engineer could not know
how to proceed. So this is the moment when the satellite engineer calls a satellite subsystem engineer, which is another engineer more specialized in each subsystem of the satellite. So it's another very important activity too. And we have the flight dynamic systems. In this particular case is where I'm working, is the part that I work in the Space Operations Center. The flight dynamics engineer performed the orbit determination, the maneuver computations to station keeping, collision avoidance. In fact, we have a lot of debris, a lot of satellites in space, and we perform with a very good frequency some collision avoidance maneuvers. And we have the satellite operators too. So the satellite operator is the person who stays in direct contact with the satellite, let's say, because the satellite operator is the person who sends the telecommands to receive the telemetry, and is another very important part of the operation too. Usually the satellite operators are technicians. We have the power and the air conditioning system. It's another part which is sometimes neglected in some way, but if we lose our power, we cannot continue our operation. And the air conditioning system is another very important part too, because we are talking about RF equipments, and usually they generate a lot of heat. And if we do not control this heat, this temperature, everything will fail. So it's something very important too. We have the model-based systems engineering. So here we are talking about simulations. We do simulations every time. Every single operation that we're gonna do, that we're gonna perform in our satellite, we must simulate it previously to know if everything is going to happen well. So we do a lot of simulation, and we use a lot of softwares to perform this. And the security, of course, we do not want that anyone enter in our facility, or it could not be a physical enter, but somebody could hack our system. So it's something that must be very, very safe in the security part. All right, and let's move on. So I will talk a little bit more about the activities that we perform. So of course that there are several activities to guarantee the entirely space system operation. And we have the space segment part. Of course, the satellite must do a lot of things, but we have the ground segment activities too. And most of them are made in the operation center. So some of the activities, one of them is the satellite tracking. So it's something that every single space center must do. We must know where are our satellites. So we are always performing satellite tracking. And of course, that when we are talking about the geostationary satellite, it's something that it's a little bit easier to do, because the satellite is in a fixed position. So the antenna is a kind of fixed. In reality, the antenna is not entirely fixed, stopped. So the antenna performs some lateral movements to track the geostationary satellite. But you can say that you can consider that it's almost fixed. And we have the low Earth orbit satellites. And of course, we have to indeed track the satellite when the satellite's moving on. So it's one of the most important activities too. We must know where are our satellites. Then we have the orbit determination. So after we track the satellite, we just receive a lot of data about satellites position over the time. So we must take this data and generate orbits based on this data. So this is the orbit determination, something that we do. This is one of the things that I perform as a flight dynamics engineer. We have to compute satellite maneuvers after we know where the satellite. So if we have to do a station keeping maneuver or satellite collision avoidance. And of course, we send telecommands to the satellite to perform several activities, to use the payload, to perform something in the onboard software, and so on. And of course, we receive the data from the satellite. which is the telemetry. One of the most important things of this is to know how is the health of the satellite, the subsystem status. So it's another very important activity that we do basically every day, every opportunity that we have. And sometimes we have to do systems ground and space updates. So sometimes we have to perform some update of a software on board the satellite. And clearly we do a lot of updates in our systems on ground. And so it's another activity that we do a lot in the Space Operations Center. And of course, the satellite is in space to do something. So we have the satellite applications, the usage of the payload. And of course, this will be different according to the satellite payload. In our case, we use our satellite to perform communications, but we could use it for different satellites to perform image acquisition, to perform weather analysis, and so on. All right, so here we already are in the conclusion. So the ground segment is a key and critical element in space operations. And as I said before, sometimes we forget that we have and that we must have a very reliable and very high availability of our ground system. And this is something very critical. As we may see, we have a lot of interdisciplinary activities. So a lot of different engineers from different areas. We have mechanical engineers, we have electrical engineers, aerospace engineers. Sometimes we think that, all right, if I want to work with satellites and space operation, I must be an aerospace engineer, and this is not real. We have a lot of different engineers, a lot of different people working together. And we have the combination of specialized professional systems, equipments, analysis tool, and complex tool chains to guarantee that our system is operating properly and that the ground segment is working well. So yeah, it's hard, but we can do it, and we can do it here in Brazil. So that's it. That is my presentation. And unfortunately, we do not have much time to stay here, but that's it. Thank you, guys.
Thank you so much, Ricardo. And I want to thank you for your time. Despite the technical issue that you had, you gave a brilliant presentation. It's very interesting to understand all of your work and this part of the ground segment and the COMAI operations. It's very interesting. I just want to see and read if you have any questions from our YouTube viewers. So let me see if we have any questions. I don't think that we have questions. So I want to thank you again in name of the PION and LASC team for your presence and of course for your time. And I'm sure that we will talk a lot about space and about SGDC, about Latin American Space Challenge, Moon, the Moon Race. Today, Paulo Vasconcelos from Brazilian Space Agency talked about the goal to put a rover in the moon, a Brazilian rover. So I think that we have a lot of things happening in the Brazilian space sector, and of course you working in the COMAI, and of course is a founder of the Pequeno Passo, is an important piece for the dissemination of the space culture and space information. So thank you so much.
Okay, Calvin, thank you for the invitation. Thank you for the opportunity. And I hope to keep in contact. And again, congratulations to this event. It's awesome. And see you soon. Stay safe.
See you soon. Stay safe also. Thank you.
Bye-bye.
Bye-bye. Hey, hello everyone. This is the closing meeting for the first day of the 2020 LASC online conference. This was a huge day. In the words that it was a lot of effort, a lot of dedication, a lot of teamwork to have a lot of keynote speakers and of course the podium sessions. And this our dedication of the team was accomplished with this successful presentation, a successful live stream. It is not easy to do a live stream, and it is not easy to do a live stream during all day with lots of speakers and teams. So I want to thank you, the PION LASC team, mainly Vitor Capacia, Mauricio Sá, Mateus, Gabriel Yamato, and João. Thank you a lot for your effort. And that's it. Tomorrow we are going to see the challenges presentation during all day, and at 8 o'clock at night we will have the award ceremony. So Yamato, do you have any words for today, please?
I just would like to thank everyone for that watched us, and for all the presenters, the keynote speakers, the podium session presenters, and our invites as well. Thank you very much, and see you tomorrow.
Yeah, it was a pleasure having you all here. Thank you again, and we see you tomorrow again.
See you tomorrow, guys. Ad Astra.